Hi guys! So I wanted to pop in and just quickly review everything we've learned so far to sum up sections 3.1 and 3.2 in our study of exponential functions. So the text we are using is Algebra with Models, A Guided Inquiry by Marian Anton and Karen Santoro from CCSU, the 2017 edition. So let's get started. Okay, exponential functions. What are they? So an exponential function is defined by an equation of the form y, or f of x, equals a times b to the x, right? We know a cannot equal 0 because that would zero our entire equation out. B cannot equal 1, and it also has to be greater than 0, right? So we cannot have a negative b. Okay, that's important. And we also cannot have a b that is set equal to 1 because 1 raised to any power, you guys, is just 1. So that would be the graph of a line at y equals a. Okay, we know that x is our independent variable, our input, y or f of x is our dependent variable, our output. A is our constant, which we call the initial value, and as we said, that cannot equal 0. It would zero the entire function out, right? Anything times 0 equals 0. And B is a constant called the constant multiplier, where it cannot equal 1 and it cannot be negative. Exponential functions have inputs that increase by a constant, while the output is changing by a constant multiplier. So we sort of talked about how that was a little bit different than a line, right? With a line, we had inputs that were increasing by a constant, while our outputs were either increasing or decreasing by a constant. So as our input was increasing, we found that we were either adding or subtracting by some constant number to go from one output to the next. And we called that our slope and our rate of change. Well, with exponential functions, we no longer have a slope, or an m, a rate of change. We now have this thing called a constant multiplier. And we're no longer adding and subtracting. We are now multiplying, right? So a little bit different than lines, and they behave differently than lines as well. Okay? And we're about to take a peek at that. Okay, you guys, so think back to when we were working with linear functions. We were looking at lines, right? When we were working with linear functions, there were two really important pieces of information that we were looking at. We were looking at the slope, the rate of change, and we were looking at the initial value, the y-intercept, right? Y equals mx plus b. We wanted to know what the slope was, the m, and we wanted to know what the b was, the y-intercept, the initial value. Well, just like with linear functions, with exponential functions, we're also looking at two really important pieces of information. And where we looked at slope for lines, now we're looking at what we call the constant multiplier for exponential functions. That's representing how our function is changing. Just like our slope told us how our linear function changes, our constant multiplier is going to tell us how our exponential function is changing, okay? So our constant multiplier is called b. If we think about that general equation, it's the b in our general equation. And this is the factor by which our outputs change. That word factor is really important. It implies multiplication, okay? This is different than when we looked at linear functions. When we were looking at a table of values for our linear functions, we either saw that we were adding or subtracting by some constant number to go from one output to the next as our inputs were increasing by a constant rate, right? We are either adding or subtracting some value at a constant rate. Well, it's different with exponential functions. We're not going to be adding and subtracting anymore. Now we're multiplying by some constant factor as our inputs increase. So this is different, right? Now we're dealing with multiplication. The constant multiplier can go by so many names, and it's really, really easy to get confused and to mix them up. They all mean the same thing, okay? So I'm just going to lay them all out on the table for you so that you know all of these names are referring to the constant multiplier, okay? Of course, it's called the constant multiplier. It can also be called the base, the factor, the multiplier. It can be called the growth factor and the decay factor, which we'll talk about in just a minute in like a few slides. We'll talk about what those mean. And of course, in our general equation, f of x equals a times b to the x, our constant multiplier is the b, okay? You'll hear me use b and constant multiplier probably the most, but it does depend on context what you call it. But all of those things, you know, that's just to say that all of those names mean that we are making reference to the constant multiplier. They all mean constant multiplier, okay? That's what we're talking about. To find the constant multiplier. So take a second and think about it, right? If you are looking at, again, let's pretend we're looking at some table of values, right? We have our inputs and our outputs. To go from one output to the next, we're multiplying by that constant multiplier, right? So let's say our constant multiplier is 2. Well, then to go from one output to the next, we would double. We'd multiply by 2. So if our input is 4, then we would multiply by 2 to get 8 for our next output, okay? So to find the constant multiplier, you take your next output and you divide it by your current output, right? You take, let's just say your second output, and you divide by your first output. So you take the output that comes, you take one output and you divide it by the output directly before it. And that's going to give you that factor, that constant multiplier that you're multiplying by every single time to go from one output to the next. So now we've talked about that, that change, right? How our function is changing, that constant multiplier. Now let's talk about that second really important piece of information, the initial value, the y-intercept. So our initial value is what we refer to as a in our general equation, f of x equals a times b to the x. And it's exactly what it sounds like, you guys. This is the starting value of our function, initial value, starting value. It's when the input is equal to 0. So for exponential equations, this is typically the value of the output when no time has passed. I don't know if you guys have noticed, but every single problem that we've done in these first two sections has to do with time, okay? Our input is either number of days, number of months, number of years. Time is passing by. So our initial value is the point when no time has gone by yet. It's our starting time, right? It's what we have when we start, how much we have before our clock starts sort of ticking, right? So however many cells we're starting with, however much money we're starting with, okay? When 0 days have passed, when 0 minutes have passed, when 0 years have passed, depending on how we're defining our variable, right? Depending on the units there. When 0 time has passed, that is the initial value. Whatever the output is at that point is our initial value, okay? It's however much we're starting with, okay? It goes by the names. Typo there, you guys. So it also goes by different names, okay? It can be called the initial value, and that's typically what I'll refer to it as. The y-intercept. So this is really, really similar to lines, right, you guys? When we were studying linear functions, our two big pieces of information were the rate of change, the slope, m, and of course, the y-intercept, b. Well, here, for exponential functions, we're also really concerned with the y-intercept. Only instead of calling it b, we're calling it a, okay? So this is the same thing. It's the y-intercept. So in our general equation, you guys, that we work with, this is our initial value, a. Okay? So we've got our initial value here, and then, of course, our constant multiplier here. So those are the two really big pieces of information that we look at when we're looking at exponential functions. So it is the point 0, a, on an exponential function, right? Our input is going to be 0. No time is going to have passed. Well, how much output do we have at that point? How much of whatever we're studying are we starting with? How many cells are we starting with? How much money are we starting with? How many whatever are we starting with before any time goes by? That's what the initial value is. To find the initial value, we've been practicing this all throughout the week. First, you need to find the constant multiplier, b. Then you can pick any point from the function. So your point would be x f of x, right? xy, x f of x. And then you plug all of that information into our general equation. F of x equals a times b to the x. You would plug in, of course, b for b. You would plug in x for x. You would plug in f of x for f of x, right? You're just plugging in your input and your output, whatever point you pick, you're plugging that in. And that leaves you ready to solve for a. Once you plug in all these numbers, you're ready to solve for a. And that's how you find it. And that's what we've been working on all week. Okay? All right, so now that we know the pieces that make up our exponential functions, let's look at how exponential functions behave, what we've been looking at this week in terms of how do these functions behave. Okay, you guys, so now let's take a second to think about how exponential functions behave, specifically exponential growth and exponential decay. So I want you to take just a minute and I want you to think back to when we studied linear functions, when we studied lines, right? So we saw that our slope, right, told us whether or not our line was going to be increasing or decreasing. So let's take a look at that. We either had a line that was increasing or a line that was decreasing. And when our line was increasing, then we knew that our slope was positive. Okay, we had a positive slope. If our line was decreasing, then we knew that our slope, our rate of change, was negative. We had a negative slope. So we saw that there was a direct relationship between our slope, our rate of change, and and whether or not our line was increasing or decreasing, the behavior of our line. It was directly related to our slope, right? The value of our slope. So there is a big relationship there. Well, just like how our line behaved was directly related to our slope, our rate of change, with exponential functions, how our exponential function behave is directly related to our constant multiplier, which is how our function is changing. It's like a rate of change once again. They are in direct relationship with one another. So let's take a look at how that relationship plays out. So we can either have an exponential functions can either increase or decrease very, very quickly, right? We know that. The amount of change is very fast, or the change is very quick, I should say. If they are increasing, they have a growth factor of b. So when I talk about growth factor, or your book talks about growth factor, or when anyone talks about growth factor, they're just literally referring to the constant multiplier, you guys. Growth factor and constant multiplier are the same. So our growth factor, our b, our constant multiplier, it occurs when our constant multiplier is greater than 1, okay? So our constant multiplier is considered a growth factor if b is greater than 1, okay? And that should make sense, again, if you take a second to think about it. So let's think about if we have an exponential function, right, and it's increasing. That's what it looks like. That means as time goes on, our exponential function is getting bigger. Well, think about what it means to be greater than 1. Let's say that our b was a growth factor of 2. That means that we're doubling. That should make sense, right? If we're multiplying by a factor of 2 from one output to the next, then we are doubling. And yeah, of course our exponential function is going to get bigger, right? If we double 4, it gets bigger. It goes to 8. If we double 8, it gets bigger. It goes to 16. So yeah, when our constant multiplier is a number greater than 1, of course our exponential function is going to increase. So that just means that we have a growth factor. Our constant multiplier is called a growth factor. Well, what if it's decreasing? If our exponential function is decreasing, then we have what we call a decay factor. And again, when we use the phrase decay factor, we're just referring to b, our constant multiplier. We're renaming it the decay factor, okay? And this time, instead of b being greater than 1, b is going to be between 0 and 1. So your constant multiplier is somewhere between 0 and 1, okay? So it's some decimal, some fraction between 0 and 1. So in that instance, our exponential function would be decreasing, okay? It would look something like that. And again, if you take a second to think about this, right? Let's say your constant multiplier, your b, is equal to 1/2. All right? So to go from one output to the next, you're cutting your output in half, right? You're going from 4 to 2 and from 2 to 1. You're cutting it in half. Well, then your constant multiplier is between 0 and 1, right? It's some fraction, some decimal, between 0 and 1. So yeah, if you're multiplying something by some fraction and decimal between 0 and 1, it is going to get smaller and smaller and smaller, right? If you keep multiplying things by 1/2, you guys are going to keep getting smaller and smaller and smaller. You're halving them. You're cutting them in half every single time. Well, that happens no matter what fraction or decimal you have between 0 and 1. It's whatever fraction or decimal you're dealing with, whatever your decay factor is, it's going to continue to make your output smaller and smaller and smaller and smaller, right? You're chopping them. So we call that the decay factor. So when we use the terms growth factor and decay factor, all we're doing is referring to your constant multiplier. And if your constant multiplier is greater than 1, then it's a growth factor because your function is going to be increasing, right? Maybe you're doubling, maybe you're tripling, okay? But if your constant multiplier is between 0 and 1, it's some fraction or a decimal between 0 and 1, then you're dealing with a decay factor, which just means your exponential function is going to get smaller and smaller and smaller as time goes by, right? Maybe you're halving, maybe you're quartering, okay? So there is, again, a direct relationship between how your function behaves and that change, that constant multiplier. If you take a look, I have two examples here, okay? Two different graphs, one representing exponential decay and one representing exponential growth. So let's take a look at the red line first. That is a graph that represents exponential decay. And if it is the graph of the exponential function y equals 1/2 to the x. And what is our b there, you guys? It's 1/2. 1/2 is between 0 and 1, so we are dealing with a decay factor. And of course, our graph is going to decrease as time goes on, right? It's decaying. We're halving it. We're chopping it in half every time we jump from one output to the next. Then if you take a look at the blue exponential function on this graph, y equals 2 to the x, well, that is representing exponential growth, right, you guys? We have our b, which is equal to 2, and 2 is greater than 1, so we are dealing with a growth factor here. And yeah, of course our graph is going to be increasing because we're doubling every single time. Our outputs are being multiplied by 2. They're increasing by a factor of 2, so they're going to get bigger and bigger and bigger and bigger and bigger. All right, so that is how our graphs, so growth and decay, really all you need to know is that they are making reference to the constant multiplier, and you're figuring out whether or not that constant multiplier is greater than 1, in which case it's your growth factor and your exponential function is increasing. But if your constant multiplier is between 0 and 1, then you're dealing with a decay factor and your exponential function is decreasing. Okay, you guys, so the last thing I want to just really quickly touch on is this idea of asymptotes, because we did not see those with our linear functions, but we do see them with exponentials. So any exponential function of the form f of x equals a times b to the x will get closer and closer and closer to the x-axis, literally forever, but it will never touch it, which is crazy, right, to think about. It's crazy to think about in your head. This means that there are no x-intercepts. So of course, if our function is never going to touch the x-axis, there can't possibly be an x-intercept. It's never going to cross it. It's never going to touch it. There's no place that this graph touches the x-axis, so we can't possibly have an x-intercept. It doesn't intercept it anywhere. This means that the x-axis is an asymptote. An asymptote, all that means is just a line that your graph never touches. So if our graph is never going to touch the x-axis, then the x-axis is an asymptote. It doesn't touch it. All right, so let's look at some graphs for a second so you can just see what I'm talking about. Here I have 3 exponential functions of the form a times b to the x, right? The first is y equals 2x. The second is y equals negative 0.1 times 2 to the x. And the last one is y equals negative 2 to the x. 3 different exponential functions. And look, all of them, as they get closer and closer and closer to the x-axis, they'll get closer and closer and closer to the x-axis, I should say, as time goes on, but they will literally never touch it. They will get closer and closer and closer to it forever, but they will never touch it, okay? And that's what an asymptote is. You can see they're all approaching it, but they're not actually ever going to touch it, which is kind of crazy. It's almost counterintuitive, but that's the way it is. All right, so it's just this new sort of behavior that we're seeing in exponential functions that we didn't see with linear functions. So I hope that this video sort of helped sum up all the big ideas that we've been talking about and seeing this week in our study of exponential functions. And if you have any questions, feel free to let me know. All right, bye you guys. Stay healthy.